All right, let's do the first homework assignment in the stoichiometry unit, which is Unit 5. So let's go to Unit 5. This is homework 5.1, and I'm taking it from page 205. All right, and I'm not going to do every single problem, but let's do a bunch of them so that you can sort of get a feel for how to do these guys, even if we don't do every one together. So let's start off with problem number 17 on page 205. It asks how many mercury atoms are in 4.2 mole of mercury. Now the way I want you to do these problems in this unit and the next couple units is always to start off by figuring out what your end label is. And so it says how many mercury atoms. So I'm going to put blank atoms as my answer. All right, it's probably going to be a pretty big number. I'll put my equals out there. Now the fact that it's mercury doesn't really matter, does it? It could be any element's atom. So we're looking at 4.2 mole, and any atom is going to have this, any element's going to have the same number of atoms on it. So I'm going to start with what my label is. Now my starting point has to be 4.2 moles, right? So let's start there and let's build this out. I know that the way I do a conversion is I always go in and I drive down the label that I start with. So I'm starting with moles. I'm going to drive moles down to my denominator. And then I'm going to say, do I know how many atoms make up a mole? Well, yeah, we learned that today. So atoms has a relationship with moles and can go up in the numerator. And my moles are canceling out. I'm left with atoms. So this is a good setup. So every 1 mole of an element has Avogadro's number. Remember, it's 6.022 times 10 to the 23rd atoms within it. That's just the definition of what a mole is, a mole of atoms is. So I've got that. So now all I need to do is do the math on it. But the way I do the math on these is I don't worry about the 10 to the 23rd. I circle it to remember to come back to it. But I just take my 4.2 moles, let's see, on clear 4.2 times 6.022 times 6.022 equals, all right, and I get 25.29 times 10 to the 23rd, right? I have to remember to go back and pick that up. Now, I look at this and I say, that is bad scientific notation. So what I have to do is divide this by 10. So it's going to be 2.5, right? Because scientific notation only has 1 digit before the decimal. And then because I divided this, making it 10 times smaller, I need to make this 10 times bigger. So instead of 10 to the 23rd, it's going to be 10 to the 24th. So 2.5 times 10 to the 24th is my answer on 17. Let's do 19. Oh, by the way, you need your periodic table. Did I happen to mention that? On 19, let's just do A and B. All right, so let's see about A. How many atoms are in each elemental sample? So I have 3.4 moles of copper. So how many atoms is the question? So once again, I've got blank atoms here for my answer. And A says 3.4 moles of copper. Again, it's totally immaterial that it's copper, but I have 3.4 moles as my starting point. I drive moles down, right? Do I know the atoms per mole? Yes, indeed I do. So I have atoms up here in my numerator. Now I know that I'm set up correctly, right? And I know this number is 6.022 times 10 to the 23rd. So once again, now all I'm doing is multiplying 3.4 times, I'm going to circle that, 6.022, 6.022, enter, and I get 20.47 times 10 to the 23rd. I circle it so that I remember to go back and get it. Again, I've got a problem, right? So divide by 10 here, multiply by 10 here. So my answer is basically 2.0 times 10 to the 24th atoms. So that was A. B, you know what? It's going to be the same exact thing. It's slightly more interesting. So let's look at B. Okay, again, I'm asked for how many atoms, blah, atoms, right? My starting point, though, is 9.7 times 10 to the negative 3 mole. It's carbon, that doesn't matter, but we've got scientific notation for the first time here. But the process is still exactly the same, right? I've drive down mole. Now I say I know how many atoms are in a mole. So now I say for every 1 mole there are, you guessed it, 6.022 times 10 to the 23 atoms. So there we are with that. Now I'm going to remember I've got two exponents to deal with here. I'll deal with that in a minute. Let's work with the coefficients first. So I'm going to say 9.7 times 6.022 equals 58. I'm going to go down here, 58.4. And it goes on, but I don't care. All right, now times 10, and I've got minus 3 times 23. And remember that because these are exponents, what I'm actually going to do is just an addition of the exponents, right? Because this is multiplication. So it comes out to 23 minus 3, or 10 to the 20th. Okay, when I simplify this down, I have to go with 5.84, right, times 10 to the, and I had to divide, so now this gets bigger, 21st atoms. All right, so there's my answer to that one. Now, let's go on and do 21, shall we? Okay, turn the page. And again, we're just working with number of atoms and moles type of thing. So let's do this, 21. And I say, my first one is neon. So let's do that. And I'm looking for the number of atoms. So gosh, once again, I'm doing this, right? My starting point is 0.552 moles, right? Do you see that? All right. And I've got the exact same structural setup, don't I? I drive moles down. I put atoms in my numerator. And I'm dealing with, let's see, neon. So 6.022 times 10 to the 23rd per 1 mole. So now let's figure this out. We've got 0.552 times 6.022 equals 3.324 times 10 to the 23rd. And that's my atoms, right? Okay. All right. Now let's go and do argon, all right? So let's do argon. Now this is a reverse, right? I'm not looking for a number of atoms, I'm looking for a number of moles. So I'm going to say blank mole. Here, and my starting point is 3.25 times 10 to the 24th. And that value is atoms, right? All right, so what I do now is I drive atoms down. I put mole up here, right? Because I can translate between these two, and I'm looking for moles, all right? And so down here I have my 6.022 times 10 to the 23rd, right? And that equals 1 mole. So I get my, I'm going to circle my exponents because I'm going to come back for those. And I'm just going to do my 3.25, 3.25, 5 times 6.022 equals, and I get 19.57. Oh, no. Okay, shame on me. Hold on. Let's go back. I say 3.25 divided by 6.022 equals, oh, now I get a whole different number, don't I? Sorry about that. So I get 0.54, basically. Okay, and then I've got 10 to the 24th divided by 10 to the 23rd. In other words, by 10 to the 1st, which is 10, right? So 0.54 times 10 equals 5.4. So my answer is 5.4 mole on that particular question. All right, let's go on and do 25, shall we? Okay, 25. How many moles of tin atoms are in a pure tin cup with a mass of 28.4 grams? So they're asking for moles of tin, right? And I've got something that is pure tin that is 28.4 grams. So my starting point is 28.4 grams. All right, now I know that what I need to do, gosh, I'm sorry, these videos are poor quality, aren't they? By golly. All right, so I know that I am starting here. I drive grams down, so there it is there. I want to get to mole. So mole can go right there. That's very good. All right, now, how do I get the number of grams of 1 mole of tin? I go to my handy dandy periodic table. I find 10, and I say, how many grams does 1 mole occupy? 118.7. So I'm going to go ahead and say 118.7, just to be ridiculously precise. And now let's go in and say 28.4 divided by 118.7 equals, and I get equals 0.239. Okay, is that right? Yep. Let's round it though. 0.24 mole. That's my answer on number 25. All right, let's see. And let's now do, we did 25, what should we do next? Let's do 35, shall we? Okay, 35. How many aluminum atoms are in 3.78 grams of aluminum? All right, so let's do that. So my answer that they're asking for is the number of atoms of aluminum, right? My starting point is 3.78 grams. So I'm going to drive grams down, right? Now, I know moles. I know I have a relationship I can figure out between moles and grams, right? And then atoms, if I know moles, then I can get atoms, right? Because I know how many atoms are in a mole, right? That's Avogadro's number. All right, so, and what we're messing with here is aluminum. So let's find aluminum. There. Oh, my eyesight's so bad. 27. We're going to say it's 27 grams per mole. 27 grams equals 1 mole of aluminum. All right? 1 mole of any element has 6.022 times 10 to the 23rd atoms in it. So now let's go in here and let's figure this guy out. I'm going to circle my exponent because I'm going to mess with that later. Clear, clear. Okay, so 3.78 divided by 27 equals 8.14. All right, now I need to deal with this, times 6.022 equals 0.843, okay, times 10 to the 23rd. All right, I need to move this, so it'll be 8.4 times 10. I had to make this 10 times bigger, so this gets 10 times smaller. 10 to the 22nd is my answer I'm going to go with. Okay, let's do one more. Let's do 49, shall we? So, oh, there's a bunch of things in 49, aren't they? Determine the number of moles of molecules in each sample. Well, let's just do one or two of these. What would we do that would be really fun here? Let's do D. All right. So I'm looking for 2.71 milligrams of carbon tetrachloride. Okay, right? Do you agree? Carbon, chloride, tetra. So we got it. Okay, so that's my starting point. And what they are asking me for is number of moles. I'm going to write my carbon tetrachloride there just for fun. All right, so how on earth do we do this guy? Okay, well, we're starting off with milligrams, aren't we? So I'm going to drive milligrams down. And from milligrams, I know how to get to grams, right? Okay, let's build this out. If I drive grams down, then I know that there's a relationship between grams and moles as long as I'm given a substance. I can work that out. All right, very good. So, all right, now let's look at this. Milligrams cancels out, grams cancels out. I'm left with moles. So that is structured correctly. Now let's populate it. I know that every 1 gram has 1,000 milligrams within it, right? All right. And then I know 1 mole is made up of however many of these there are. So let's work that out. Carbon and chlorine. I have 1 carbon and 4 chlorine, right? I know each carbon has 12 grams per mole. I know each chlorine has, well, I honestly don't know, so let's go look. Chlorine, 35.4, all right? Okay, 12, 4 times 35.4. I wish I were good at math in my head, but let's do this. 4 times 35.4 equals 141.6. I add those up and I get 153.6. Okay, so there are 153.6 grams in 1 mole of carbon tetrachloride. All right, so now let's get in and do the math, all right? So we're going to say 2.71, 2.71, okay, divided by 1,000, okay, and then we're going to say divided by 153.6, 153.6 equals, I get 1.76 times 10 to the negative 5. Now, does that make sense? That's a really small number, and that's a really small amount. So I would think that that makes pretty good sense, that that should be about right. Okay, and it is structured right. It's in correct scientific notation, so let's go with that. All right, very good. So those are just a couple problems that are present in your homework for tonight.